Oi, boa tarde a todos. Vocês me escutam?
Yes.
Crazy. Bom, perdona-me, eu vou introduzir em português. Sim?
Sim. Sim.
Está bem?
Está bem.
Eu queria começar agradecendo ao Ramses por aceitar o nosso convite para fazer parte do seminário. E eu acho que o agradecimento tem que ser quase que de joelho, porque eu descobri que esse rapaz, ele virou diretor do instituto dele há poucos dias, né, poucos meses, e ele terminou a chefia do departamento dele, então eu imagino que a quantidade de trabalho dele está gigante. Então, Ramses, muitíssimo obrigado por tudo isso. O Ramses, ele é pesquisador titular lá na Universidade Nacional Autônoma do México, que é uma das principais universidades da América Latina. O Ramses, ele fez a graduação dele em atuária, o mestrado em ciências matemáticas e depois, isso tudo pela UNAM, e depois ele fez o doutorado dele pela Universidade de Bath. Mas Ramses, ele está envolvido com um monte de projetos, né? A área de pesquisa, que eu acho que é a principal área de pesquisa dele, é em estatística bayesiana não paramétrica, mas ele tem muitas coisas, muitos trabalhos interessantes com processos estocásticos aplicados, com séries temporais. Ele já orientou um grande número de alunos, né? E alguns deles eu já vi que continuaram o caminho de pesquisador, assim como o Ramses tem feito. Ele já tem mais de 40 artigos publicados em revistas muito conceituadas na nossa área. E ele não se dedica só à pesquisa, isso que eu acho mais interessante. Acho que é fruto do DNA jovem dele. Ramses está envolvido com um monte de coisa, além da direção do instituto dele, que é recente. Ele foi cofundador da seção não paramétrica da ISBA, né, que é uma seção bastante ativa, que organiza periodicamente um congresso em estatística bayesiana não paramétrica. Ele é membro do conselho diretor da Sociedade Latino-Americana de Probabilidade Estatística, que eu acho que está vinculada, né, à Bernoulli Society. Ele já foi presidente da Associação Mexicana de Estatística, e apesar de todo esse grande montoeira de trabalho que ele faz, o Ramses aceitou falar para a gente. Então, eu sou realmente muito grata por sua presença aqui, por você ter aceitado o convite. Eu lamento que não seja ao vivo, aqui em pessoa, para a gente tomar um chopinho depois do seminário. Tá? Muito obrigada, Ramses.
Thank you, Rosângela. Well, thank you, everyone. I think I'll do the talk in English because I have zero Portuguese in my... I can understand what Rosângela said, and I thank her for the nice introduction. It's a pleasure to be with all of you guys. It's a shame I cannot be there, but Rosângela is not going to escape a proper invitation. I hope in the future we are able to pass these difficult times and actually be with you all in that beautiful place. So what I want to talk about today is a research work I have done together with Maria Fernanda. I don't know if you can see this. Maria Fernanda Gil Leiva, a PhD student at IIMAS-UNAM, and Theodoro Nicoleris, who is at the University of Athens. The idea is a very simple idea, so we have a lot of time for questions if you want to stop me, or if you want to finish, whichever is the technique you're using in this forum. And so I'll start now. The first idea I want to remind to many of you is that the idea of exchangeability. If you will think about the property, this symmetry property is very linked with Bayesian statistics. Indeed, if you think about a sequence of events that are physically independent, the best way to apply a model and to learn statistically about a sample that we're taking about that model, the basic one, when we don't have other things about information about the dependence on the models, is the exchangeability. And so the property goes back to the very simple idea that sampling does not affect the distribution. So you can see these two sequences here have the same distribution if they are exchangeable, meaning the order that is represented with a row here, the order does not affect the distribution of the actual sample. And that's the easiest way, and there are a lot of foundations behind this idea to link it with Bayesian parametrics, in particular with with Bayesian statistics, and in particular with Bayesian non-parametric statistics. If you think about the old idea behind this concept that goes back to the Finetti in the 30s, is that a sequence of this sort can be characterized as a conditionally IID sample given something. And that's something that is the unknown about the sample that we are modeling and can be seen as the limit of empirical measures almost surely. So this idea goes back to the very simple concept that sometimes we go into statistics when we think about, for instance, if we think these are normal random variables dependent on a parameter, say the mean, and then we mix over the mean, then that leads us to exchangeability. But when we are not conditioning on a particular property as the mean can be, but conditioning on the whole uncertainty about that sample, meaning we do not restrict our modeling only to those nice distributions that have a very nice shape, like the Gaussian distribution, then we have a general concept. So, and that in that general concept, the Finetti ensures these decompositions that we have. I'm just recasting in this very short illustration here. So, given that we have exchangeability, is and only if and only if there is a measure here denoted by mu in the space of all probability measures that we are denoting with this funny plot here on a particular space. So think about the samples Y, taking values on the real numbers, so whatever Polish space you are modeling your data in, and then think about all the probabilities that can be constructed on that support, say S, and that includes all the multimodal, all the shapes, right? So if you think about that, then what exchangeability is telling us is that given that information, you can think of these random variables as IID, and then links to the idea of having a sample from a phenomenon you're studying, right? So in that context, it's very strong, and it has defined a whole area of statistics, Bayesian statistics, in particular Bayesian parametric statistics, when you study the whole non-parametric model, the whole shape, and from a mathematical point of view, from a probabilistic point of view, it goes back to the simple idea of modeling random variables, mu again, but instead of tossing a coin and obtaining a 0-1, or tossing a coin and obtaining a particular number, like in the Gaussian case, you obtain a real number. In the univariate Gaussian case, here you toss a coin with this law, mu, and then you obtain a random probability. Say, if you want to think of a density, this can be a realization of that, other can be something like that. You can have all sorts of shapes if you are consistent and full support in that modeling context. So let me go ahead with this idea. So then the idea becomes very simple: how we model random probability measures. And I've seen in the previous sessions you have spoken with some other, you have listened to some other speakers, Peter Mueller, I think Rafael Argento was also here, where they spoke about models that fall into this class, how to construct Bayesian parametric models. And the main idea goes back to the seminal paper by Ferguson in 1973, when he introduces the canonical model, which is the Dirchlet process, say the Gaussian in the case of random probability measures, right? So in that case, many things have been done, and many developments to cover some drawbacks of the Dirchlet process, or to generate models more adequate for certain kind of phenomena, have been developed. So the thing I will speak to today in this brief talk is about that kind of constructions and going into that direction. So the idea that has been used a lot in the construction of discrete random probability measures is this decomposition that we see here, right? If we think of a discrete probability, like the Poisson, the binomial, the negative binomial, we can always decompose it like this, right? Certain weights like the Poisson weight in certain locations. For instance, if you think about the Poisson distribution, well, these weights would be the weight of the Poisson distribution in 1, 2, 3, 4, 5, whatever, right? The support of the Poisson distribution. Of course, in the general case, if you think of weights and locations being random, then this becomes a random element, which turns out to be a random probability measure, which is very well studied and very well suited for Bayesian parametrics. So the idea here is that these weights, of course, they are in 0, 1. And these in particular live in the support that we are interested in. Say, if we are observing a time series of stock exchange, probably you live in the positive real number, so this would be the positive real line, or whatever you're looking at. And since these are weights, they have to add up to 1. And they have to add up to 1 if these are random in probability 1, meaning the probability of this, let me see if I can handle this here, not very nicely, is equal 1, right? So this is the model, the typical model that we use for discrete random probability measures, where the atoms and the weights are independent as well. This is a sequence that adds up to 1 almost surely, and this is a sequence of random variables with this support. And so the idea then becomes you can think about the model, and this falls into a class that is well studied in statistics, the class of mixture distributions, where ideally you would have that this element here, this weight here, this proportion, matches the proportion in the real phenomenon you are studying with that observation in particular. Meaning the probability of obtaining this value is W1, the probability of obtaining θ2 is this value, and so on. So I don't know, this is a bit late, but let me try to fix it. So in this case, something very important that is not necessary, but it helps a lot in the computation, is that the measure that we are going to assume for these random variables here has to be diffuse. Meaning if I sample from this θ value, then there is no probability for ties, right? This probability 0 of repeating the new values. Think of this, for instance, if you're in the positive real line as the gamma distribution, or if you're in the reals or the Euclidean space as a normal distribution, for instance, right? Of course, depending on the situation you are modeling, can be more complicated. One of the ideas of basic ideas of Bayesian parametrics is that the support of this random variable here, that this random probability measure, has to be complete, has to have full support. In bold terms, it says that any distribution can be modeled by this random probability measure. In other words, we are able to recover whatever true of the model that we are trying to develop, we are trying to discover, unveil about those particular phenomena that we are studying. So this is a very interesting topic, and of course there are many things about it. It's not only full support, you also need consistency. We are not going to speak a lot about that topic here, but the idea is then that if the support of these atoms is the same as the support you are studying, and then the support of this, in principle, random probability measure will be equal to the support of all random probability measures on that particular space, say the reals again. So this is interesting because then we are looking, whatever we are building a new model of this sort, we would like this property to be satisfied, right? If this is not satisfied, then we are not in a particular case. For instance, if you take this to be the Poisson distribution, of course you cannot replicate a distribution on a particular support of theta's where you have multimodality. So it won't be the same as having a full support. So one of the properties one of the conditions for this support property when you are starting from this decomposition, and I have to remark here, there are many constructions of random probability measures so that we are going to go through the talk. But of course, the one that we are looking now is this very simple representation of a random probability measure. So if you start from this representation of a random probability measure, then the condition of full support translates into this condition here, which is essentially a condition that bounds the fact that the weights add up to 1 for any epsilon positive, right? So this is the thing we have to prove for any chosen weights we are going to define, and then we are going to do that. A typical construction that probably you're familiar with is the so-called stick breaking construction, a construction for the weights. This is for construction for the weights, okay? A particular construction that is very famous is the stick breaking way, where you start with a stick of unit 1, and then you take a random variable in 0, 1, and then split the value on that, and the remaining part you're going to split it again with another random variable, and so on, in such a way you have that the weights can be decomposed in this form like this, right? So this is a very helpful manner to construct weights that add up to 1 almost surely. Of course, there are some conditions on these random variables. We haven't said anything about them other than the fact that they take values on 0, 1, and they lead to values of wi, the sequence of w's adding up to 1. So if you think about this decomposition, the remaining bit, if you add up to the weight j, say, the remaining bit can be written by this expression, this product expression here. So they add up to 1, essentially, if this remaining bit goes to 0 almost surely, which is satisfied if and only if this expectation goes to 0 in this condition. So there is a very simple condition to check that the weights add up to 1. So the question is, how do we construct the weights? We already said there is a stick breaking construction. It's not the only one, of course, but this is the one we're going to study in this talk. But with the particular selection for these random variables that we call them length variables of the stick breaking construction. So with the particular conditions on these variables, then we recover models. Of course, this is a very well-known property. Once you define the weights like this, then the support property we had before reduces to this expression here, which is also relatively easy to check. There are many models in the literature, and the known one, for instance, is the so-called Dirchlet process, where these length variables are IIB from a beta distribution 1 beta. Bear in mind they are independent and identically distributed. If we remove the fact that they are identically distributed, then we have other classes of random probability measures. There is a class called the 2-parameter Poisson distribution, and that is the fact that they are the length variables are independent when where the scale, well, one of the parameters of the beta distribution depends on that factor, right? And this leads to another huge class of random probability measures that we are not going to study very thoroughly in this talk. But there is a lot of discussion in the literature because many of the models that have been applied since 95, that the MCMC methods for the Dirchlet process or mixtures of Dirchlet process that we're going to see later were discovered. Many models have been introduced, but the problem is which of them are feasible for computing, feasible for estimation. And these two models lie in this realm of being very applicable, right? Say the Dirchlet process, or the more general case, the 2-parameter Poisson Dirchlet process that includes as a particular case the Dirchlet process when sigma is equal to 0. Okay, so there are many models. One of the models that we have been studying with other colleagues is the models that are Gibbs type priors, that we call them. In a way, these distributions can be determined in many ways. One of the ways that can be defined is through the predictive distribution. And probably I have to stop here a bit. Since you are starting from a exchangeable sequence, the exchangeable sequence can be characterized by the random probability measures and then integrating out. Or you can just think about this symmetry also being preserved when you are modeling the predictors. So that means that if you take one value of a sequence of size n, say, and you have infinite exchangeability, then the predictive is going to be the same no matter what is the value that you remove and condition on the rest. So there is a huge class of models characterized like that, and one of the best classes, I would say, is the Gibbs type priors, which has been studied a lot in the literature for many people, for colleagues and I as well. And in a nice paper by Favaro that turned out from a thesis of Consuelo Nava with Igor Brunster. Also, I think in that paper is Antonio Leoy, Nipote, and EYT. They managed to discover a representation of the stick breaking for this class. Of course, the representation of a stick breaking construction, as we go back here, is very nice because we know that the random probability measure is very easily I'm going back. It's very easy to present as this random sum, right? So that allows to do a lot of sampling methods and a lot of very nice applications also for other classes of processes, right? So this representation Favaro et al. Found in that paper essentially tell us that the length variables of the stick breaking representations are no longer independent. So don't fall in any of these class. So they are dependent, and the dependence is the representation, because it's just a representation of possibly many representations. The representations they found is essentially that the distributions of the length variables are given conditionally on this manner with this expression here, which is a complicated expression because it depends of the density of a sigma stable density function, which is underlined here. So, and here as well. So it depends how are you able to actually do this in real life, which sometimes complicates a bit the applicability. I'm not saying it's impossible, but this is just a class. But it's a very interesting class because it's very general, and of course includes the two classes that I mentioned before and others as well. So there is also a very nice paper. So actually, the one I was citing here, I think is this one here, where they do the Gibbs type the stick breaking length dependent length weights representations for the general class of homogeneous normalized random measures with independent increments. So this class is a very huge class of distributions on the set of distributions, and the idea is very simple. You normalize a completely random measure and then do inference with that, and that becomes this very general model that is studied in a paper also by Antonio Liu, Igor Punster, and Lancelot James in 2009. So, and that class also has this representation for a very rather complicated, even more complicated than this expression for the weights. So what I'm trying to get at is when you start from the pure decomposition of random probability measures as random weights and at random locations, weights and locations are independent. So in that case, there are many ways to construct the weights, and many of the models that are out there that we know, these classes that I'm underlining here, they have, complicated or not, expression for these length variables of the stick breaking representation. So the first idea then is much of the research in this direction has been built from I want to recover some of the classes that I already have, like homogeneous normalized complete random measures, with these representations, so they can be applied in the many other ways that are applied random probability measures, whatever, regression, time dependent, or whatever of the applications, clustering, even you think you've seen some clustering also in the previous talks. So I want to focus here in a class that it has a very appealing view when you're doing sampling. And this is, of course, we have the Dirchlet process that many of us we know. And then we have another process that is called the geometric process, which is a very easy simplification, say, of the Dirchlet process. So in the Dirchlet process, let's try to start with, we have the length variables are IID, beta, and then you have the stick, you have the weights with the stick breaking construction, and then you have that the expectation of these weights are order. And then they have a size bias random order, which is interesting because with that size bias random order, you're able to reconstruct many of the things we use for clustering. The EPPF that we are going to probably speak about later on, and other things that we use for clustering a lot, if you are focusing on a particular clustering idea. So on the counterpart, you have the case where these random variables, these length variables of the stick breaking representations are equal to 1. Here we just said lambda with a particular distribution. Here we say beta distribution. So you have these length variables, then the weights are very simple, right? Are geometric weights. You think this is a geometric formula for the weights. They are order not only in mean, but always order, almost surely order, which means that it doesn't matter which is the choice of the random distribution here, the random number, they are going to have decreasing order. And this order is very important because when you are modeling things like mixture distributions, if you go back to the theory of mixtures, it's always a problem when you have that you don't have a decrease in weights. Essentially, you move into a problem that is called identifiability that later on falls into the numerical problem that is called label switching. And that means that you are jumping in between parameters in your estimation, and you can never decide which is the best parameter. And of course, that was a discussion that goes back in the 2000s, in the 90s, and there were many papers trying to fix up finite mixture models in order to attain that identifiability, or in order to control it to make inference. But in this case, this is somehow reduced by having the weights order. So we are trying to look in these two classes, and they are string classes. One has random weights. Of course, they have to have certain behavior, because otherwise they wouldn't add up to one. And the other one is they are order. And there are many things, there are many papers we have discussed in these lines, but in a very simple manner, the Dirchlet process is very good for clustering, when you're thinking in the clustering that implies the repetition of the labels. And in the geometric process, it's very good for density estimation. It's very good to fit, because you don't have that label switching problem as you would in other models. So there are these two models in the literature that have been used, and they are very interesting in their own sake. And of course, there are some good things about one another. Both of them have full support, and both of them, of course, have the weights adding up to one. The consistency issues has always been a problem, because the contraction rates for the Dirchlet process, for the geometric process, is not as satisfactory as you would get for the Dirchlet process. But still, you have that is a valid model for inference. And if the question is, if we are able to mix this into a model that has both, that would be very desirable, because you will be able to control this dependence and allow the model that you are applying to switch between one and another, and to accommodate best to whatever you're modeling in the phenomena. So these are examples. They are very old, but I like these two plots here. They have the same data, which probably you won't see, but it's an histogram that is behind these density estimates. And the difference here in these two plots is you have a dynamic mixture of Dirchlet process, and then you have 100 iterations, which are drawn here after 10,000 MCMC estimations, MCMC realizations. So this is the the burn-in estimation of 100 realizations after a burn-in period, using the classical way to estimate the density using the Paul-Young scheme, right? So in other ways, this is the first 100 iterations without any burn-in of the geometric process. So you can see how they adapt immediately to the locations without getting into trouble, like still is happening here even after 10,000 simulations. So this is the density estimate of both of them. And if you think about it, this is a very nice thing to do when you're doing classification based on the density, which it has its own meaning, because then you would say that the weights somehow represent the population frequencies. And that's a very interesting way, the way that Feller in his 43 paper thought of mixture distributions. So the way we're going to do this, again, I repeat, trying to build up a model that includes these both sides, is through a particular decomposition of these length variables. And it's worth mentioning that this geometric model won't fall, it doesn't fall into the class of normalized completely random measures. And that's important, because then it's a model that is outside that world, and it's a model that is very useful for estimation. So then with Theodoro Nicolaris and Maria Fernanda Leiva, we discovered this way to do it. We use an old method to construct Markov chain Monte Carlo, Markov chains with marginal beta distributions. And that is a very easy way that we have used a lot. Basically, the idea behind is to use the symmetry of a reversible model and to condition properly to get the marginal that we desire. That's the idea behind this method. And then we use that in order to have marginals that are beta distributed, but also with a tweaky that allows us to have both distributions. Let me try to introduce this model here. So you start with a beta distribution for B1, then you introduce the dependence on the model with this binomial distribution here through this latent variable xi, and then you compute the posterior distribution using these values of the length variable at state i+1 given the latent variable, and that's also a beta distribution. If you have this model constructed like that, if you sample and you can try it out in our program, then you will see that the marginal, the invariant distribution, because in this case it's an homogeneous Markov process, is a beta distribution. So that's a very easy way to construct a process with marginal distribution. It has been explored by Luis Enrique Nieto Barajas in a paper with Stephen Walker in 2002 and using survival analysis. And I have used it to construct diffusion processes in a paper with Stephen Walker in 2009. But this is the dependence, how it goes. But it's a very easy way to construct a model that has beta distribution, with beta marginals. So if we construct, again, this now are going to represent length variables for us. So if we represent these length variables like this, using this beta Markov chains that we just shown, then this condition is satisfied, meaning the weights add up to 1, and they have full support as well. So they are valid to construct a model for stick breaking, even though they are not independent or identically distributed, but we already know that there are models with that representation, is the paper by Favaro et al. So about this Markov chain, we have this parameter, kappa, that if we go back to this construction, appears in the dependence, is the n, if you want, of the binomial distribution, and that leads to a parameter only, an integer value parameter here only, in the Markov chain model we are constructing. So that parameter kappa is going to say it all, is going to say everything, because when that kappa goes to infinity, we are going to degenerate in a random variable, obtaining the geometric weights. And when that goes to 0, we are going to have the IID beta distribution. And if we take alpha equals 1, beta equals beta, then we have the Dirchlet process. So in a way, we are putting a length variable models that recovers both worlds in a single model. And that's an interesting thing because we already proved that that model, it has full support, has weights adding up to 1. And this is just a simple plot that we are doing related to that, to the conditional density to the transition density, if you want to think about it, of going from the value at i+1. In other words, the one step ahead transition density. So if you fix the value you are conditioning on 0.4, you see how it degenerates when kappa goes to infinity to the value that it has only one value in that random variable, or you have the independent case in the case of the Dirchlet that we are approaching. So these are simulations of the process of the Markov chain, we are saying, and of course when the value is very big, the kappa value is very big, you have weights. This is the distribution of the weights. You have the weights that are the order, they converge to the geometric. Otherwise, you have weights like you would have in the Dirchlet, say in this purple realization here. You have somehow order in mean, but you don't have order all the time. And these little jumps here are those to blame about the label switching then when you are doing MCMC applications. So the beta binomial process, we express it like this. It's essentially a model. It's a random probability measure where the weights are constructed with the stick breaking construction, but where instead of having the length variables as simple as in the case of the Dirchlet process, we have this beta binomial chain. Okay. And as I was saying before, when kappa tends to infinity, you recover the geometric process. Otherwise, if kappa tends to 0, you recover the Dirchlet process. Okay. And this is just the condition to allow to have the process well defined. So then again, we can look at many things when we look at random probability measure. One of the things that are more popular are the number of groups, because since they are discrete random probability measures, then you have ties, and those ties create a distribution on the random partitions. And then if you sweep on a particular fixed number of groups on those random partitions, then you have a distribution on the number of different groups, which is very useful for assessing many of the properties of random probability measures, in particular those that are almost surely discrete. It's good to mention that you can do also that with those that are not almost surely discrete. Okay, so then you have this decomposition, as we mentioned before, and this random variable that is implied by this construction represents the number of distinct values on the sample, or in other words, the number of different atoms. So we have here a lot of atoms, but those that repeat, here I think we have, this is an example with 4 groups. So those are the ones defining the groups, right, in this particular example. So again, if we look at the distribution for Kn, for the beta binomial stick breaking prior, where different values of kappa, then we realize that when it's 0, then we have the similar behavior as we do for the Dirchlet process. And then when it goes to infinity, you have the Dirchlet process. This is a very important thing to look at, because it essentially tells us how much are we able to capture new values of the process, and how much are we able to control the distribution of number of groups. So an effect that has the geometric process is that to represent a particular group or a particular location, you need a lot of weights, since they are ordered, and with one random variable you define the all weights, all of the weights. You need a lot of those weights. Unlike the Dirchlet process, you need less. So there is a nice trade-off in this situation here. So we are going to put examples, of course, with the mixtures. If you think the classical mixture model, which essentially is mixing this random distribution with a random probability measure to end up with, say, in this case, for instance, a random density that has weights in particular locations of the kernel you've chosen, in this case, the normal kernel. So this is the classical mixture of normals. Of course, we are going to infinity here. It's not a finite mixture of normals, but that is a product of the random probability measure we are applying in the mixture. So in that case, something that is typically done is that the different parameters imply different values of this, and therefore different groups. Okay, so this is just the picture of that. Essentially, you have different kernels here. You have, I don't know, I think it's 1, 2, 3, 4 kernels, and you have different values in this case, right? Of course, you can you have also these confounding random variables, and what it typically goes is that you have more mixture components that those necessarily to represent a particular shape in a density. And that's exactly this plot. So we have here 6 values with 3 modes, which are like this, but those modes are somehow confounded like this. So the density estimation then is a model that is very simple. Again, as we have the models before, we have, for instance, these weights being beta binomial, and the locations just conjugate to that normal model. And then we look for a Gibbs sampler. So the Gibbs sampler, I can recast and probably sit down here to explain it, but for those that are familiar with a bit with Bayesian or parametrics, there are many methods. We are applying here a method we are familiar with, and we always trust because it always works, at least for us, which is the slice method by Stephen Walker, 2007, that you can take the variation of it with the paper by Kali et al. and control the decreasing weights to make it more efficient as well. So, and then with that Gibbs sampler, you obtain posterior of the weights and posterior full conditionals for the weights and full conditionals for the locations. The full conditionals for the locations, that does not change. So what essentially is going to change is the conditional for the weights, because the weights are those that have the dependence and those that are changing. So the idea of having a beta binomial model is that makes the weights also, when they are dependent, also very easy to sample from the posterior. So in that case, we have this estimate. That is the density estimation of the predictive distribution. And you also have the posterior number of groups. So once you put a value on the number of groups, that can be done controlling this kappa parameter a priori. And then you observe data, and then you obtain the posterior distribution on that number, which is usually what is used to assess the number of groups in a particular sample. So here is an example. We just took alpha and beta equals to 1. The alpha makes sense because we are trying to compare it with the Dirchlet process, but the actual model actually works for other values. And so this would be a total mass parameter for the Dirchlet process equal to 1. So in the case we have beta 1 and kappa 0, then we have the Dirchlet process. So you want to think about these values here. These are the Dirchlet process. And if you go with kappa 1000, for instance, here, or infinity, then you recover the geometric case. So these are just examples. So you can see how there is a bit of improvement in the Dirchlet case over the Dirchlet. I'm sorry, in the geometric case over the Dirchlet. Improvement is minor in this area. But what is important is that you're recovering this model. So I want to explain and go back to that plot where you saw two realizations, the 100 realizations, the first 100 realizations for the geometric, that they appear to fit very well the model in the first 100, and the other of the Dirchlet that gets some confusion. So of course, when you start with an MCMC, there are many things that can alter that starting point. For instance, you are putting a prior that favors different number of groups to those observed, or you put a prior that only is going to consider those observed, but you're very far from discovering new things. And depending on those values, you will need the randomness of the weights or not to attain a fast convergence. So what this model is using is the fact that you can switch in between two worlds and try to compromise the best model in that particular realization of the process. So that's the whole idea of having this model, besides the theoretical interesting point that you have the limit, the geometrical, the limit, the Dirchlet process. Okay, so this is the posterior distribution. Of course, as I was telling you before, the posterior distribution, you need more weights to represent a value of the geometric than the distribution of more weights. Also is correlated with a k of kappa bigger, number of distinct points bigger, which in this case is represented here with this green histogram. And in the case of the Dirchlet, we know that the prior distribution of Kn is very big. So somehow, if you are close to when you define the model, you're close to the real value, then UMCMC is going to converge faster. It's going to be nice. If you're far, then you need a different thing. And there are many models for that. One example is the stable model that has a prior that is flatter, and then you can converge faster to those values. So I want to conclude a very basic idea of this simple talk to allow for questions and to recast a bit of the idea. So there is a class of stick breaking process that recovers the well-known priors presented, the Dirchlet process and the geometric process, and that class allows you to have a better MCMC behavior of the sampler, and that's been proven also in many ways in the papers. Some colleagues and I have written about the geometric, but also we acknowledge that the geometric is points for clustering. So you have to combine that into a single model, which is what this is doing. There are many realizations. This is just the tip of the iceberg, if you want to think about it. There are many realizations that goes into dependent length variables. There is a very comprehensive theory that we have developed with Maria Fernanda in her thesis in this archive paper, submitted already, which is a paper where the length variables are not longer this beta binomial, but they have a different dependence and exchangeable sequence. And they have very good links and very good properties that all depend on the type probability. So it all boils down to the type probability of a discrete random probability measure, which is an interesting point because essentially you can classify many of the properties, theoretical and also sampling properties, by only studying the type probability. So I think I'm on time for the 45 minutes I think I was given. So thank you very much for listening. And of course, I'm open for questions. Thanks.
Thanks so much. Very nice job. Very nice. Someone has questions, comments? I have some. No. Very nice for me because you put some things about the Dirchlet process and the others that I have no idea. because I was not so studied this process so deeply as I need to do. But when you define this beta binomial way to define the weights, what kind of ordination we put in the weights in this case? It's like the Dirchlet process, or it's in the means, or you are ordinating in a properly? No.
That's a very nice question, and it's a very interesting one. I replied. So essentially, what you're saying is which kind of ordering of the weights are you imposing by allowing this model, right? And it's a property we look at in the paper. We sort of put a result on that. There is a way to prove that the expectation of the weights being in order depends on a factor depending on this kappa random variable. Mm-hmm. Okay, and that essentially tells us that you can control the weight through the kappa parameter, the way the probability of being order is assigned, and that result is a nice result because it allows us to do a lot of tuning when you're applying these models. We would have liked that for this kind of dependence we have that probability in a stronger result. In this model does not happen. In the other model, which is I consider a richer class, that I said was in the archive paper. In that model, we can control it very nicely, and then we have the improbability. We have the results, and of course that gives us the way of controlling the ordering, and that means that you can tune that in a mixture. This hasn't been done in a way because when many of the solutions, for instance, for the label switching problems in the 2000s, in the 90s, were focused on ordering some parameters or ordering the ways to attain that. But by doing that, you were changing the model a bit. So we are not doing that because we are starting from a model that has full support. So we are not going to change that model. But we can control the weights and, of course, the way it adapts to a particular ordering mechanism. So, and that is, to our view, to our point of view of mixtures, of clustering, of Bayesian statistics, of particular mixture models, the best way you can control this in applications, right? Because otherwise, there are many applications and many uses of DPM models. These are process mixture models, where you have a lot of confounding factors, and then you end up tuning a lot of things that you shouldn't have tuned if you have understood the model well from the beginning. And this ordering that you are mentioning is the whole point of it, and we can control it in these models. On that question, there are many things open, I think, that are still to be discovered, but a very nice result in general, where these length variables are no longer beta binomial, but are exchangeable, is in that archive paper I mentioned.
Okay, thank you. There is another question from Guido.
Okay, let me try to open this thing because I now is choosing the weights more. I can read it now. Is choosing the weights more impactful than choosing the base measure? Of course. It is. The base measure is it has a lot of impact in the support, okay? But you have to combine it in a way. But if you want to think of a model of a Bayesian parametric models, the weights is the whole point, right? So the difference between the Dirchlet and the geometric, and I like to always put this example, is like if you compare, when you're modeling a random variable on the real numbers, you compare the normal distribution and the student t distribution. Okay, so one has the bigger, fatter tails. We put more weights on the tails than the other. Both of them are full support, right? Both of them cover the real line, but they cover it in a different way. So that's what is going on with these models. I'm not saying that one model is better than the other, but you have to have control of the weights. And in the case of the Dirchlet, you have full support as well as in the geometric, but the mass you are allocating to different sets is different. Of course, we cannot look at it very nicely because we haven't come up with a way to model the finite dimensional distributions of the geometric. That would be nice. That's something to discover yet. But But if you're able to do that in many ways, for instance, comparing the KN, comparing some functionals, you're able to sort of tell what's going on without actually looking at the final dimensional distributions. But of course, if you control, there is always this trade-off in I would say all of statistics, right? Dependence against random flexibility in distribution. If you control the P0, you are able to sample a lot from it. But if the weights are not rich enough to make you sample that value when you need it, and this is important, then you won't be able to recover that, right? Because of course, when you're modeling things in the real, you cannot put a uniform distribution, right? So, and that's the point. That's the whole point of it, I think. That's the whole point. You need to be able to control the weights in order to pick up the value that you want from this P0. Of course, the results are going to be depending on this P0 as well, right? This is important. See, there are some discussions to be held there, but I think otherwise you would only model things with a fixed number of weights. So, sorry, with deterministic weights and P0. And you can also do that. It's not doable. You can do that, but then you won't have the flexibility to adapt this mixture well. We have done that in the typical courses we give about Bayesian parametrics. We made them to do that, to realize that if you do that, you're not able to discover the right value that you need to represent that particular peak in your distribution. And of course, that worsens a lot when you go to higher dimensions, right?
Is there some other question? I have some. When you use the Dirchlet process, there is a kind of finite representation of the Dirchlet process just for computation. Then there is a kind of k numbers in the mixture just to implement the Dirchlet process.
Yeah.
Prefix as the number of components in the mixture.
Yeah.
Is there a theorem related to this choice of the number of components just for implementation in this case?
Yeah. There is a general result that allows you to truncate for the weights. That does not depend on the weights of the length variable, being independent. So you can apply that theorem also to this one. I'm not really friendly with the fact of truncating. I think it's not the best. If you really are applying a Bayesian parametric models, you need to be able to discover whatever is out there that you haven't been able to observe. And I think truncating, in principle, forbids to do that. Of course, if you truncate to a very large number and the weights are somehow decreasing, then you are there because you have a computational bound that you cannot go beyond that anyway. But you can do that here as well. We prefer to use the slice. The slice has some limitations as well, and there are many new methods as well that you can employ here. We are just constructing a new model. But of course, many of the algorithms that are out there and are applicable to stick breaking representations, you can apply it here. The predictive is another story is yet to be told. In this case, you don't have the Polya-Orn that you would have for the Dirchlet. The weights are horrible and depends of horrible mixtures in general. So horrible special functions like the hypergeometric function. And that makes it really difficult to be useful. So I think the useful bit here is to apply the stick breaking. And that's what we are selling. And I think it's a nice idea. After years of applying BMP models, I like it because you're able to gain the two worlds. The dense, if you want to see it in a very applied viewpoint, you get the clustering that is very rich in the Dirchlet, and you get the density estimation that is very, very nice of the geometric. And if those two combine, you get the best model that is for an application there. And of course, this is, as I was saying, just an example of a very general theory that is being developed and is about to finish the thesis of Marifer, who is the one to blame for most of the things done in this line of research. And then she has a lot of contributions in that direction. And I think it's very important to underline that. Of course, I wouldn't be able to do the whole theory on my own.
Okay. Guido, thank you for the talk.
Thank you.
I have another question from Josemar Rodrigues. Hello, Josemar.
Yeah. Did you try to replace the binomial for the negative binomial? Thank you, Josemar. Yes, we did. Actually, there is a. I can say there is a master thesis of a guy who is doing that. It's a nice example of course, if I go, I don't know if you see the mouse here when I'm pointing. You see the mouse, Rosangela, in the presentation?
No, I can't.
Okay,
no.
Let me try to escape it here and then go to the presentation. Here, if you replace this distribution with a negative binomial, then you also can construct with a different dependence here, a model that has beta marginals. And it's a very interesting model, by the way, that I have studied with other people in continuous time. It coincides with a branching process representation, which is very nice. And that model, you can also use it here. Why not? It's just going to change the whole idea is going to change only if you use that particular model, it's going to change the full conditional on the weights. And might be difficult, maybe not. I don't think it would be difficult at all. It's a nice example. And that's what this guy has done in his master's, and he has done it in very general way. He has focused a lot in the clustering. And you can look at it because we are lucky to have the thesis UNAM, and that's a gossip I'm telling you all, guys. If you go to thesis UNAM, there is a web page where you can scratch the thesis of all the students that are open, and that's going to be open soon as well. You can look at that as well, and that's a very nice application because he's looking more like into the clustering world. They're very rich, but again, I insist in that question. I think it's important. This is just an example, right? This is just an example of many possible models that you can construct. The one that we attain in more general case is the one I again pointed out in that archive reference I gave. If you want, I can just go back here so you have it. Let me see. So in that archive, in this archive paper, you can have the full picture of another type of dependence, somehow much richer than this one. I wanted to explain this because it's simpler to get the idea without going into the full theory. And the other one, of course, is a full theory and has a lot of maths as well, so it's more difficult to embrace it in one single talk. But you can look at it in that paper that is in archive, and hopefully in a paper that is published somewhere soon.
Oh, some more questions? No? I guess we can stop here. Thank you. Like to thank you again. Very nice work, very nice job. Thank you so much for accepting my invitation. I hope next time it will be here in Brazil, in Belo Horizonte, for you to meet my colleagues and the students that are present here. Thank you so much. I see you next Friday. Have a nice weekend, everyone. Bye.
Have a nice weekend, everyone. Thank you for attending the talk.